Microsoft quietly shut down one of the most advanced quantum research facilities on the planet. No press conference, no announcement, just silence. And inside that lab, scientists had been working on something that doesn't fully fit inside our current understanding of physics. The findings weren't buried, they were published, but almost nobody noticed. Stay with me, because what they discovered inside that lab rewrites something we thought we already knew, and it started with a particle that shouldn't exist. Most people know Microsoft as the company behind Windows and Office, the software that runs on billions of computers, the tools that offices, schools, and governments depend on every single day. That is the Microsoft most people picture, but there is another Microsoft that most people never see. Since around 2016, a quiet research division had been operating out of the University of California, Santa Barbara. It wasn't hidden behind locked doors or classified clearances. It was hidden in plain sight, the way most serious science is. It had a name, it had a website, it published papers, and almost nobody outside of a small circle of physicists paid attention to it. It was called Microsoft Station Q. No product launches came out of it, no software updates, no announcements at tech conferences, just researchers, whiteboards, long calculations, and a question that had gone unanswered for nearly 90 years. The goal of Station Q was not to build a faster computer. That framing misses the point entirely. What they were after was something more fundamental, something that sits underneath the question of computing altogether. Yeah, they were trying to find a particle, a very specific kind of particle. One that had been predicted mathematically back in 1937, but had never been physically confirmed to exist in the way they needed it to. That particle was connected to a man named Ettore Majorana. Majorana was an Italian theoretical physicist, quiet, brilliant, and by most accounts deeply unusual. In 1937, he wrote a paper proposing a new kind of particle, alas, one that behaved differently from everything else physicists had ever studied. Most particles have an opposite, an antiparticle. An electron has a positron. They are mirror images of each other. If they meet, they destroy each other completely. Majorana proposed something strange. He asked whether a particle could be its own antiparticle, whether something could contain both sides of that equation inside itself. A particle that, in a sense, was already complete. The mathematics worked, the physics allowed it. But proving it in a real experiment was something else entirely. And then, in 1938, Ettore Majorana disappeared. He boarded a ship from Palermo to Naples. He was never seen again. No body was found. No explanation was ever confirmed. He simply vanished. The same year, his most unusual idea was still fresh on paper. The particle bearing his name remained theoretical for decades. Now, here is where it becomes relevant to computing, and relevant to what Microsoft was actually building. What do you think drives a company like Microsoft to spend years chasing a particle from a 1937 physics paper? Drop your thoughts in the comments. I'm genuinely curious what you think is behind this. The biggest problem in quantum computing today is not speed. It is not size. It is errors. Quantum systems are extraordinarily fragile. The information stored inside them, called quantum states, can be disturbed by almost anything: vibration, heat, electromagnetic interference. Even the act of measuring a quantum system can destroy the very information you were trying to read. Every major quantum computing program in the world is fighting this same problem. Google, IBM, Intel. They are all building systems that require enormous amounts of error correction just to function reliably. For every useful qubit, the basic unit of quantum information, you may need dozens or even hundreds of additional qubits just to catch and fix the mistakes. Majorana particles offered a different path. In theory, if you could engineer a system where quantum information was stored across two separated Majorana particles, one at each end of a tiny wire, that information would be protected in a way that ordinary qubits are not. It would be spread out, non-local, impossible to disturb without affecting both ends simultaneously. The environment could push and pull at the system, and the information would remain intact. This is called topological protection. And it is the reason Microsoft built an entire research program around a particle that, at the time they started, had still never been definitively observed. They hired world-class physicists, built specialized equipment, collaborated with universities across Europe and the United States, and after years of work, they announced results. The scientific community looked at those results carefully. And what happened next was not what Microsoft expected. To understand what Microsoft's team was actually trying to build, you need to spend a moment inside the quantum world. Not the version of quantum physics that shows up in movies, not wormholes and parallel universes. The real version, which is, in its own way, far stranger. Everything around you is made of particles. The chair you're sitting on, the air you're breathing, your own body. All of it, at the most fundamental level, is made of tiny things that follow rules we didn't write and still don't fully understand. In the world of classical physics, the physics of everyday objects, things behave predictably. A ball thrown through the air follows a path you can calculate. The rules are consistent. They make sense to our intuition. In the quantum world, those rules change. Particles do not have fixed positions until you measure them. They exist in multiple states at the same time. They can be connected across distances in ways that have no classical explanation. And every particle, as far as we know, has an opposite, an antiparticle with the same mass but opposite charge. When a particle meets its antiparticle, they annihilate. They disappear in a release of energy. The universe, in a sense, cancels them out. This is standard physics, well established, confirmed across thousands of experiments. Ettore Majorana's idea broke this rule. He proposed that certain particles might be their own antiparticle, meaning they carry no net charge. Meaning, if one met another of its kind, they would not necessarily annihilate, because they are identical in every meaningful way. They would simply pass through each other, or interact in ways that are deeply unusual. For decades, physicists suspected that neutrinos, the near massless particles that pass through matter almost without interacting, might actually be Majorana particles. Experiments have been searching for a specific type of radioactive decay that would confirm this. So far, no definitive proof has been found, but condensed matter physicists, scientists who study the behavior of materials, realized something important in the 2000s. You don't necessarily need to find a Majorana particle traveling through space. Under the right conditions, inside the right materials, something that behaves exactly like a Majorana particle can emerge. Not a fundamental particle from deep space, but a collective behavior of electrons in a specially engineered system that mimics all the same properties. These are called Majorana zero modes, or sometimes quasiparticles. The conditions required to create them are extreme. You need a semiconductor nanowire. A wire so thin that thousands of them laid side by side would not equal the width of a human hair. You need to cool this wire to temperatures far below anything found in nature on Earth. Colder than the surface of Pluto. Colder than empty space in most parts of the universe. Then you need to apply a precisely calibrated magnetic field and pair the nanowire with a superconducting material that allows electrons to flow without resistance. If all of these conditions align, theory predicts that Majorana zero modes will appear, one at each end of the wire. Stable, protected, holding quantum information in a form that the surrounding environment cannot easily disturb. Microsoft's Station Q was designed to make this happen. The engineering challenge involved is almost impossible to overstate. Every element of the system has to be controlled at an atomic level. The materials have to be grown with near-perfect precision. The interfaces between different materials, where the semiconductor meets the superconductor, have to be clean at a scale measured in individual atoms. Research groups at Delft University of Technology in the Netherlands, at the University of Copenhagen, and at several American universities were all working on similar systems. There was a genuine international effort. But Microsoft was unique in the scale of its investment and in its explicit commitment to topological qubits as the foundation of its entire quantum computing strategy. This was not a side project. This was the plan. And that is what made the next development so significant. Because when Microsoft's team published their results, and when other physicists looked at the data, what they found raised a question that cut to the center of everything. Had they actually found what they were looking for? Or had they found something that merely looked like it from a distance? Science moves slowly. That is not a weakness. It is the point. A result means nothing until other scientists look at it, test it, challenge it, and either confirm it or find where it went wrong. This process, peer review, replication, criticism, is what separates science from guesswork. It is slow, it is sometimes uncomfortable, and occasionally it produces moments that the entire field remembers. 2018 was one of those moments. A team of researchers affiliated with Microsoft's quantum program published a paper in Nature. For scientists working in quantum physics, Nature is one of the most respected journals in the world. Getting a paper published there means it passed through a serious review process. It means the editors and peer reviewers considered it significant enough to share with the global scientific community. The paper claimed to present strong evidence for Majorana zero modes in a semiconductor nanowire device. The signal they were looking for, a specific feature in the electrical conductance of the nanowire, called a zero bias peak, appeared in their data at exactly the values the theory predicted. It looked like confirmation. Headlines in science publications described it as a major step toward topological quantum computing. Microsoft's approach suddenly seemed less like a long bet and more like a genuine breakthrough. Then other physicists started reading the data more carefully. Researchers at Delft University of Technology, the same institution that had been running its own nanowire experiments for years, began raising questions. The concern was technical but important. The signal Microsoft's team had observed, the zero bias peak, was not unique to Majorana zero modes. There was another, far more ordinary phenomenon that could produce an almost identical signature. It is called an Andreev bound state, a localized quantum state that forms near the interface of a normal material and a superconductor. In simple terms, there were two possible explanations for what they saw in the data. One was the exotic, revolutionary explanation, Majorana particles. The other was a well-understood, far more mundane quantum effect that had been studied for decades. To distinguish between them, you need to look at more aspects of the data. You need to examine the system across a wider range of conditions and confirm that the signal behaves in the specific way that only Majorana modes would behave, and not in ways consistent with Andreev states. Critics argued that the 2018 paper had not done this thoroughly enough. And further, that some data which might have complicated the picture had not been included in the published version. If you're starting to see how unusual this situation is, a major corporation, a prestigious journal, and a contested discovery all colliding at once, subscribe. Because what comes next involves a decision by one of the world's top scientific journals that almost never happens. Microsoft's team pushed back initially, but the scrutiny continued. More independent researchers examined the work. The concerns did not go away, they deepened. In 2021, Nature made a rare and significant decision. The journal officially retracted the 2018 paper. It is one of the most high-profile retractions in recent quantum physics history. The retraction notice acknowledged that the paper had not met the standards required for its central claims. Specifically, that the data presentation had been incomplete, and that the conclusions about Majorana zero modes went beyond what the available evidence could actually support. The authors, some of the most qualified physicists in their field, accepted the retraction. This moment is important to understand correctly. A retraction does not mean fraud. It does not mean the scientists involved were dishonest. In this case, it reflected something more subtle and more instructive. The enormous pressure that surrounds quantum computing research had created conditions where the desire to find a result may have shaped how that result was presented. Governments were watching. Investors were watching. Competing laboratories were watching. The race to demonstrate a functional quantum advantage over classical computers had been building for years. Microsoft had made a very public commitment to topological qubits. The incentive to find positive results was enormous. This is not unique to Microsoft. It is a tension that runs through all high-stakes scientific research. The need for funding, the pressure of competition, the weight of expectation, all of it creates subtle forces that can influence how data is interpreted and presented. Microsoft did not collapse after the retraction. They restructured. They brought in additional oversight. They changed how results would be reviewed internally before publication. And they kept going. Because the underlying idea, the theoretical foundation for topological qubits, had not been disproven. The question had simply not been answered yet. And in 2023 they tried again, with a different approach and a different outcome. After the retraction, Microsoft's quantum team faced a genuine reckoning. Not a crisis of funding, not a shutdown. A scientific reckoning. The kind that asks a research program to examine its methods, its standards, and its definitions before it publishes another word. What came out of that period was something more careful, more deliberate, and ultimately more credible to the broader scientific community. In 2023, Microsoft's researchers introduced what they called the Topological Gap Protocol. This was not a new discovery on its own. It was a measurement standard, a defined, reproducible test that a device would need to pass before anyone could claim it had entered the topological regime. Think of it like a checklist. Before a bridge is declared structurally sound, engineers run specific tests under specific conditions. They don't just look at the bridge and decide it seems fine. They measure, they stress test, they follow a protocol. The Topological Gap Protocol was Microsoft's attempt to bring that kind of rigor to Majorana detection. The protocol required measuring multiple properties of the nanowire device simultaneously, across a range of conditions, magnetic field strength, temperature, voltage, and confirming that the results matched theoretical predictions in a way that could not be explained by ordinary Andreev-bound states. It was a higher bar. Deliberately so. The results from applying this protocol were published in Physical Review B, a peer-reviewed journal focused specifically on condensed matter physics. The response from the scientific community was noticeably different from 2018. Not unanimous agreement. Science rarely produces that cleanly. But the criticism was more measured. The concerns were more specific. And several independent researchers acknowledged that the methodology represented a genuine improvement. Some physicists still had questions about whether the topological regime had truly been reached. The debate continues, but the tone had shifted from skepticism about the data to substantive scientific discussion about what the data means. That is a meaningful distinction. Alongside this, Microsoft made a broader announcement about the architecture they were pursuing, a topological qubit chip they had been developing in parallel with the basic science. The design relied directly on Majorana zero modes as the physical basis for storing quantum information. Here's why that architecture matters. Every quantum computer currently operating, Google's Sycamore, IBM's Eagle, the systems being developed by IonQ and others, uses what are called physical qubits. These qubits are real, but they are fragile. Any disturbance from the environment, thermal noise, stray electromagnetic fields, even random quantum fluctuations, can cause an error. A single corrupted qubit can cascade through a calculation and destroy the result entirely. To deal with this, engineers use quantum error correction. They encode one logical qubit, the qubit doing the useful computation, across many physical qubits. The redundancy allows errors to be detected and fixed on the fly, but this comes at a steep cost. Current estimates suggest that a single reliable logical qubit may require anywhere from dozens to over 1,000 physical qubits to support it, depending on the error rate of the hardware. This is the wall that quantum computing is currently pressing against. Building more physical qubits is possible, but scaling the error correction machinery to match is enormously complex and expensive. Topological qubits, if they work as theorized, sidestep a significant portion of this problem. Because the quantum information is stored non-locally, distributed across two Majorana zero modes separated in space, it is inherently more resistant to local disturbances. The environment has to disturb both ends of the system simultaneously to corrupt the information, which is far less likely than disturbing a single point. This means fewer errors to begin with, which means less error correction overhead, which means a cleaner, more efficient path to the logical qubits that actually perform useful computations. Microsoft's roadmap suggests that topological qubits could allow them to reach meaningful quantum computation with far fewer physical qubits than competing approaches. If that is correct, it is not just a different path to the same destination. It is a faster path. The rest of the industry was paying close attention, but the question of what a truly functional quantum computer could actually do, the real-world implications that sit beneath all of this physics and engineering, is where the story becomes something much larger than any single company or research program. Step back from the nanowires for a moment. Step back from the retracted papers and the measurement protocols and the engineering challenges. Think instead about the problems that currently have no solution, not problems that are difficult. Problems that are, in the most precise sense of the word, impossible for the machines we have today, no matter how many processors you add, no matter how much memory you install, no matter how long you let them run. These problems exist, they are real, and some of them involve things that affect every person on this planet. To understand why, you need a simple model of how classical computers work. At the most fundamental level, every computation a classical computer performs comes down to bits, ones and zeros. Everything your phone does, every transaction a bank processes, every weather forecast, every search result, all of it is built from sequences of ones and zeros, manipulated according to precise rules, billions of times per second. Classical computers are extraordinarily fast at this, but they are sequential in a way that cannot be fully escaped. When a classical computer faces a problem with a very large number of possible solutions, say finding the optimal arrangement of thousands of variables, or simulating the behavior of a complex molecule, it has to explore those possibilities in a way that scales badly. Double the size of the problem, and the time required doesn't just double. It can grow exponentially. Problems that would take a modern supercomputer longer than the age of the universe to solve are not hypothetical. They exist in chemistry, logistics, cryptography, and material science right now. Quantum computers operate on different principles. A qubit is not locked into being a 0 or a 1. Through a property called superposition, it can exist in both states simultaneously until it is measured. This allows a quantum computer to, in a sense, explore many possible solutions at the same time rather than one after another. Combined with a second property called entanglement, where the state of one qubit is directly connected to the state of another, regardless of the physical distance between them, quantum computers can perform certain types of calculations in ways that have no classical equivalent. The practical implications of this are not small. In medicine, one of the most difficult problems is drug discovery. Designing a molecule that interacts with a specific protein in the human body in a specific way requires understanding quantum mechanical interactions that classical computers can only approximate. These approximations lead to enormous amounts of trial and error in the laboratory, billions of dollars spent, and years lost testing compounds that fail. A sufficiently powerful quantum computer could simulate molecular behavior at the level of precision that chemistry actually operates on. Researchers at institutions including MIT and various pharmaceutical companies have already begun exploring what this might mean for diseases like Alzheimer's, for antibiotic-resistant bacteria, and for cancer treatment. In materials science, the potential is equally significant. The design of better batteries, the kind that could make electric vehicles cheaper and more practical, involves quantum mechanical processes at the atomic level. So does the design of more efficient solar cells. So does the search for room temperature superconductors, which would revolutionize how electrical power is generated and transmitted. These are not abstract scientific goals. They are engineering problems with trillion-dollar consequences. Think about this the next time you charge your phone, or read about a new cancer treatment, or hear about climate change. The limits of what we can do about these problems are connected, in a direct and concrete way, to the limits of the computers we have available to solve them. What is being built in these labs is not separate from the world you live in. It is pointed directly at it. In cryptography, the implications are already being treated as urgent. The National Institute of Standards and Technology, NIST, spent years running a global competition to develop new encryption standards specifically designed to remain secure against quantum computers. Those new standards were finalized in 2024. The fact that governments and standards bodies are already preparing for the post-quantum era tells you something important. The people closest to this technology believe it is coming, and they are not waiting. A quantum computer powerful enough to break current encryption could compromise banking systems, government communications, and private data on a global scale. This is not a distant theoretical risk. It is a near-term engineering timeline. What Microsoft was building at Station Q was a foundation. Not the finished structure, the foundation. A new type of qubit that, if it works as intended, makes the path to that finished structure shorter and more reliable than any other approach currently being pursued. The lab is now closed. The research has been integrated into a different phase of the program. But the question this raises, about what was found and what it means, leads directly to the final part of this story. Laboratories close for many reasons. Sometimes a program fails and the resources are moved elsewhere. Sometimes a project succeeds and the work shifts from discovery to development. And sometimes the phase of science that a lab was built for simply reaches its natural end. The foundational questions have been explored as far as they can be with that particular setup, and what the work requires next is a different kind of environment entirely. When Microsoft reorganized its quantum hardware division in 2024, it was not framed as a failure. And looking at the arc of what Station Q actually produced, that framing holds up under scrutiny. The lab had accomplished something real. It had taken a theoretical concept, a particle predicted in 1937 that no one had been able to engineer into a working system, and produced physical evidence, increasingly rigorous and increasingly reproducible, that the underlying physics was sound. Not proven beyond all debate. Science rarely works that way, but demonstrated to a degree that shifted the conversation from whether it was possible to how to make it reliable. That is a significant transition. The retracted 2018 paper, viewed in the context of the full program, looks less like a fundamental failure and more like a calibration. It showed the scientific community, and Microsoft itself, where the standards needed to be higher. The 2023 Topological Gap Protocol was the direct result of that lesson. It was more rigorous precisely because the earlier work had been challenged. This is how science is supposed to work. It is not always comfortable, it is not always fast, but the self-correcting nature of the process is what gives the results meaning when they eventually come. What Microsoft left behind is not just a collection of published papers, it is a foundation that other institutions are actively building on. Research groups at MIT, at Delft University of Technology, at the Niels Bohr Institute in Copenhagen. They are all working with nanowire systems, topological states, and Majorana physics. The European Quantum Flagship Initiative, funded by the European Union, has made topological quantum computing a core research priority. DARPA in the United States has funded related programs under its broader quantum technology initiatives. Microsoft itself has not stepped away from quantum computing. Its Azure Quantum Platform continues to develop. The topological qubit roadmap remains active. The company has been transparent that it views this as a long-term project, not a product cycle measured in years, but a fundamental shift in computing infrastructure measured in decades. And there is something important in that long-term framing. The history of transformative technology is full of moments that looked, from the outside, like setbacks. The first transistors were fragile and unreliable. Early Internet protocols failed constantly. The first attempts at MRI technology produced images so unclear they were nearly useless. In each case, the underlying physics was sound. What took time was the engineering, the long, unglamorous process of translating a scientific principle into something that works reliably, at scale, under real-world conditions. Quantum computing is in that phase right now. The physics is established enough to know that the machines are possible. The engineering is the hard part, and the hard part takes time. What Station Q contributed to that process, the years of experimental work, the refined measurement protocols, the published findings on topological states and physical devices, will be part of the field's foundation for a long time. The researchers who worked there are now distributed across academia and industry, carrying that knowledge forward. The lab is closed. The question it was asking is not. And here's the part of this story that most people don't consider. Every system you rely on that involves a computer, your bank account, your medical records, the power grid, the satellites that make GPS possible, was built on assumptions about what computers can and cannot do. Those assumptions are about to change, not suddenly, not in a single announcement, but steadily and in ways that will matter at every level of society. The research happening in these labs, contested, careful, slow, and serious, is the beginning of that change. Microsoft's Quantum Lab was closed, but the silence it closed into is not the silence of something that ended. It is the silence of something still in motion. Because what is happening right now in the global race to build the first truly fault-tolerant quantum computer? The race that involves not just Microsoft, but Google, IBM, China's national quantum programs, and a growing number of startups you have never heard of, is something almost no one is fully tracking. And the country that crosses that finish line first will hold an advantage that no other technology in human history has quite matched. That story is next